an inverse problem, a very interesting inverse problem with very interesting applications that concerns elastography. Elastography is a technique that serves to detect elastic properties of tissue. So you have a tissue, you don't know which are the elastic properties. This can be illuminated with the solution of an inverse problem that we are going to present now. Why do we need to know many times the elastic properties of a tissue? Because it serves to detect a tumor. A tumor is much harder than the healthy tissue. So in a tumor, you have different elastic coefficients, different elastic properties, and this is seen in the equations that you are observing here in these coefficients, mu and lambda. This is the Lamé system. It serves to compute the displacements of the points of the tissue, and if in the tissue there is a zone, a region in which you have a tumor, then the coefficients mu and lambda are going to be higher, much higher than in the rest of the tissue. So if you knew mu and lambda, you would be able to compute, by solving this problem, how the different points of the tissue displace, which is the displacement at each point. But obviously, in principle, mu and lambda are known, because you don't know if there's or not a tissue inside. So this is the inverse problem. The inverse problem consists in computing, if possible, mu and lambda from properties of the solution to this system. And the property that you observe, is this is the observation, is which are the values of the stress, the normal stresses, on a part of the boundary. So the elastographic process consists in fixing phi, which are the displacement on the boundary of omega, fixing phi, and then measuring, observing the values of the stress generated by phi. This is what the professionals call a stress captor. Stress captor permits to compute, as we are going to see, mu and lambda, and then once you have mu and lambda, you are able to produce something like this, an elastogram in which the values of mu and lambda indicate that there is something inside, there is a tumor inside, it serves to detect at a given moment the situation. This is the case of a glioblastoma. In the case of the glioblastoma, things are much more complicated because Lamé system is not appropriate for this situation. Because in Lamé system, you are assuming that the displacements are isotropic. There is no privileged direction. In the glioblastoma, this is not the case. This is not the case because the brain has white matter and gray matter, and white matter is elongated tissue. So there are some privileged directions, and the system to solve, in fact, is a system much more complicated. Well, it is linear. It can be linear because the displacement is small, but it is more complicated. There are many more coefficients, and the things are more complicated. But the principle is the same than here. The principle is the same as here. So this is a glioblastoma detected by an elastogram that has been detected by solving an inverse problem that is not exactly the same that I'm going to show, but is similar. Elastography has also other applications. It can be also applied to the detection of arteriosclerosis. Arteriosclerosis can be defined as the thickening or hardening and also the loss of elasticity in an artery. And in this case, we are looking at elastogram associated to the carotid arteria. Okay, and this is the diagnosis has been made because we have generated waves, hydrodynamic resonance waves, and we have detected it by solving the problem, and we see that there is a region which the arteria has become hard, very hard, and this is the origin of the problem. Okay, what have we done with this problem? Well, we want to compute mu and lambda from these values, the stress. So we have converted the inverse problem in a direct problem in some sense. We consider this cost. Lambda is the value of the observed stress tensor, normal stress tensor. So we consider this cost and we try to solve this cost with respect to mu and lambda. This is the idea. The idea is simple. It's not simple to compute the minimal of this quantity because the system is not much sensible to mu and lambda. We have to perform very precise computations in order to get a good result for this problem. And also there is something to add that is not completely natural, but has to be added. That is a restriction on mu and lambda, and more precisely, a restriction on the total variation of mu and lambda. In order to ensure that this problem has a solution, we have to restrict to coefficients mu and lambda with some regularity, and the regularity is here. We need total variation bounded uniformly for mu and lambda. Okay. In fact, this is equivalent to penalize the cost with the term in which we have R. We have the total variation. Another way to look at this problem is to add here a penalization term, and this penalization term has to be something related to the total variation. See? Yes?
What do you mean by total variation? Is it the gradient of the...
Essentially, it's the L1 norm of the gradient. Essentially, it is this. It's a little more general than this, but essentially, to get an idea, this is you have mu, you have lambda, you need mu and lambda with the gradient in L1, and you measure the norm in L1 of this. More or less it is. In fact, your question is interesting because, in fact, when we are solving the approximate problem, when we are discretizing and solving an approximate problem, it is immediately satisfied because for mu that is constant by triangle, for example, you have this. And with a constant R that only depends on the triangulation of the mesh. So, in fact, for practical computations, this condition appears almost immediately. Okay? This is the first thing that I want to say, that this problem, once we restrict mu and lambda to this condition, has a solution. And then we have been able to construct the solutions mu and lambda as I am going to show in a moment. Let me, however, indicate that there is an open problem here. What happens if we don't impose any condition on the total variation of the coefficients? Are we still able to prove that there is a solution to the problem? It is not easy because observe that this is a hyperbolic system. So for a hyperbolic system, regularity is not ensured, and the situation can be much more complicated than in parabolic or dissipativity system. So it is not easy to get the existing result for a system like this. Anyway, it would be interesting to be able to prove an existence, a general existence result. Okay. Let me show an example, a numerical experiment. This is the domain. This is a mesh of the domain, sufficiently large number of triangles, and this is a target. This is a target. This is a situation that we want to discover. This is a target. What I have done is to fix the target. Once I have fixed the target, I have measured the observation, and I have used the observation. The observation is measured here in the semicircle, semi-Laua circle, and I have used this observation to solve the inverse problem. And we have been able to find the solution, as you see. We have had to use a very specific algorithm for the solution of the minimization problem because, as I have said, the situation in a hyperbolic system is not the best possible. So we have tried to get the result with several algorithms, and we have seen that the best results have been obtained with this version of a quasi-Newton algorithm after many computations of the gradient. But anyway, we have been able to recover the values of mu and the values of lambda that were there. Even we have done the same with two tumors. The same thing. We have fixed this target. We have computed the observation associated to this target, and we have used this observation, and we have got, with a lot of efficiency and very precisely, the values of mu and lambda in both cases. So it is okay. Huh? These are the histories of the cost, the values in both cases. So you see that after some iterates of the well-chosen algorithm, we are able to solve the problem. Okay? Okay, this is the first part. And now I'm going to pass to the second part of the talk, of the course. Okay. I'm going to speak now of Navier-Stokes. Several problems concerning Navier-Stokes problem, equations. Control of Navier-Stokes from several viewpoints. This is the system, the Navier-Stokes system. Already the existence of a solution, as you know, is a non-trivial problem. We know that there exists, in the interesting case n equal to 3, we know that there exists a weak solution, but we don't know if it is regular. And in principle, it is not unique if you relax the definition of a weak solution. There are many problems, many theoretical problems concerning the existence. But we are going to speak of control. So we will try to look at the controllability or optimal control problems related to Navier-Stokes. There exist many reasons to try to solve control problems for the Navier-Stokes equations because there are many applications. For example, boundary controllability or boundary control in general for the Navier-Stokes equations is related to the minimization of drag or the turbulent behavior of a fluid around an obstacle. Here you have practical situation when you have, for example, the wing of a plane. Without suction of the on the wing, we have a very disordered and turbulent behavior of the particles near the wing. It begins to stabilize if you make some suction here. If you increase suction, then the fluid begins to adhere to the wing, and the situation is much more comfortable. And so, well, this is a way to control the behavior near the wing as a practical application of controllability problems. So. Contamination, pollution, is another source of applications of control of Navier-Stokes or Navier-Stokes-like systems, like this one. This is a system where you have a density, a mass density that is not constant, coupled with Navier-Stokes equations with variable rho, and all this is coupled to an equation of an additional variable, which is a pollution density. And we have put a control here in a small part of the domain, and we try to get good properties of the whole system. We want to have, of course, psi small at time capital T, because if psi measures the contamination, the good situation is this one. This can be applied, for example, in the study of the Great Pacific garbage patch. That is an immense patch of plastic that is in the ocean near Hawaii, and occupies about 3 times the surface of France. So this is a terrible patch of plastic. And there is a project which is called the Ocean Cleanup Project, Ocean Cleanup System, that was initiated in 2013, in which an artifact, a structure, a large structure, is trying to collect the plastic in order to accumulate all plastic in some points and then transport them to the coast. The situation is, well, this is the structure, this is a part of the structure, and you see that there is a kind of skirt pending from the structure designed to collect the plastic. This is the way it operates. There are 2 ships here that are moving the structure and collecting all the plastic. And all this leads to a lot of problems that can be solved by looking at the control formulation. Where do we start to do this? Which is the good shape to get the plastic, the optimal shape. Which are the accumulation points, all this? I forgot to put here the website page, the address, but if you look at ocean cleanup in internet, you will find a lot of information over this. And it is very interesting because in real time you can see what are they doing now, what are they getting. The project was, in fact, started at about 2016 or 17, so there have been many advances. And many of the problems that they try to solve can be, in fact, modeled with the Navier-Stokes equation of some variance. Sorry? I didn't want to go to the details, but in fact, this is a first attempt to model the situation. in fact, the good equations are primitive equations for the ocean, because they are two-dimensional and not three-dimensional. And it is better to work with them. But anyway, you have to use a different mass density and a function of psi to measure the pollution that is produced. Yeah.
What about the winds?
Sorry?
The winds, the problem of winds.
The winds.
Wind. The first model of the plane. The wind plane.
Ah. What yeah.
Do you think that the free structure model is better here than the Navier-Stokes model?
I have supposed here that the wing, well, I have simplified, of course. The wing is fixed, the structure is fixed, there is no vibration, so this is a wall, in fact, from the viewpoint of fluid mechanics. You have the equation, it has to be solved in a fixed set, and what I have add here is just the value of u at h, because it models suction only like this. But of course there are many other models that can be, because in fact, yes, the wind, the vibrations of the wind, there is motion, there's a motion, but
There is some transmission between the structure and the fluids.
yeah, well, yes. But for the moment, I have fixed that the position of the wind, and this is the problem that I have presented, okay? Of course, yes, a fluid structure problem, because the wind can move. You say, if you see, I have taken here a reference system that is fixed with respect to the wind. So the particles move, the fluid particles move, but the wind is fixed, okay? Okay, well, I'm going now to speak to a particular control problem for the Navier-Stokes equation that concerns two objectives, bi-objective control problems for stationary, in order to complicate only a minimum situation, stationary Navier-Stokes equations. So, in a simplified form, I have written here the equations, and I have considered two objectives corresponding to two targets, U1D and U2D. And we want, as I have said before, to get at the same time small values of J1 and J2. How can we do this? Well, of course, it is impossible to get a minimal, to get a couple F1 and F2 that minimizes both functions, but because they can be incompatible. It can be two incompatible tasks. So we have to look for an equilibrium. An equilibrium can be of several kinds. One of them is what is called a Nash equilibrium. A Nash equilibrium is a couple F1, F2, such that we have two properties concerning each of the components. The first property is that J1 attains a minimum with respect to F1, and J2, the second property is that J2 attains its minimum at F1, F2 with respect to F2. Okay? So at F1, F2, the value of J1 cannot be worse than a value at another F1, at F1 prime, and at the same time, a similar property for H2, for J2. We cannot have a worse value here for J2 if we take another component, another second component. This is a visualization of what happens with two very simple functionals. These are the isovalues of J1, these are the isovalues of J2, and this is the Nash equilibrium. It is a point for, with the property that I have said. If you vary one of the components, then you cannot improve the value of the required function. Okay? What we have done is just to prove that there exists Nash equilibrium. This is not trivial. It is much more. It is delicate. The proof of the result is delicate because of the nonlinearity of the equation, and overall because of the non-uniqueness of the solution that is not ensured in general. It is only ensured for very large viscosities. So it is not a trivial task, but we have been able to prove that there exists Nash equilibrium for this equation. And we have been also able to characterize, in the sense of optimal control, the Nash equilibrium. More precisely, we have proved that a Nash equilibrium necessarily satisfies a system of this kind. You are probably very familiar with systems of this kind in which we have a coupled set of equations. First, you have the state equations, then you have something that is called the adjoint equations that are linear and that give another variables, and you have a Pontryagin or some, it is usually called Pontryagin characterization of the control that relates the control to the solution of the second equation, of the adjoint equation. This is the structure, the usual structure of an optimal control problem when you characterize the solution. And in this case, since we have two controls and two criteria, the things are a little bit more complicated because you have two adjoints, each of them associated to the control. But it can be done, and you can also in this case get a characterization of the Nash equilibrium. This is interesting because it gives you two things. First, it gives you a myth. First, it gives you a criterion to discard some controls to be a Nash equilibrium, but also gives an algorithm in order to compute it, because very easy to implement algorithm consists in fixing the control, computing the state, then you have the state computing the adjoint states, and then when you have the adjoint state, recomputing the controls, you get in this way a fixed point algorithm that many times converges. It's not the only one. You can do things that are better, working with the expression of the derivatives and all this, but it works. It is a first attempt to compute the Nash equilibrium. And we have applied algorithms of this kind in order to get the solution in this problem. This is a canal. Again, this is a canal. The fluid goes from the left to the right. And we have added, we have used here 4 small rectangles. These are omega 1 and omega 2, little omega 1 and little omega 2. And these are O1 and O2. And what do we want to do? We want to have something with some particular properties here in O1 and something with particular properties in O2 working with controls restricted to little omega 1 and omega 2. More precisely, we want to have this. We want to have something close to 0 here and something close to a rotated field in this part. Again, I say that we want to work with the controls supported by this small rectangle and this another rectangle. This is equivalent, in fact, to work with boundary controls, because in fact, what we want to know is which are the values of U to put here and here in order to get this structure. And for technical reasons, it suffices to enlarge a little bit the domain to fix a control supported by these two small rectangles, and to take then the restrictions to the boundary. Okay. Anyway, we have been able to get this with the Reynolds number that is not a moderate Reynolds number, that is not small. You see that it is possible to solve the Nash equilibrium problem and to get controls here and here that produce, as you see, something that is close to the rotated field that I have shown before, something that is small here. Okay? Well, it works. There are many other computations where we have tried to do the same things and it works. So you see that it is possible to control from the bi-objective viewpoint Navier-Stokes. Other results and other problems. Okay, it would be possible to compute other equilibrium of other kinds. I mean Pareto equilibrium. What is Pareto equilibrium? A Pareto equilibrium is a kind of equilibrium that is completely different from Nash equilibrium. In the case of these two functions, J1 and J2, these are the Pareto equilibrium. The Pareto equilibria are characterized by couples F1, F2, such that no other couple, no other different couple is able to improve at the same time J1 and J2. Okay, this is the definition of Pareto equilibrium. It's a couple that cannot be improved at the same time from the viewpoint of J1 and J2. And these equilibria can be characterized using Euler-Lagrange theorem, can be characterized as those that connect through a curve, these two minimum of J1 and minimum of J2. It is interesting also, I prefer to show it, it is interesting also to see which is the behavior of the values of J1 and J2 at Pareto equilibrium. At Pareto equilibria, we get these results for J1 and J2. In the plane J1, J2, we get these results. As I said, there are results that cannot be improved in both directions. And I have profit to compare here and to mark which is the location of the Nash equilibrium in this plane. So the values furnished by Nash equilibrium have nothing to do with this characterization of Pareto equilibrium. Okay, this could be also done for Navier-Stokes and would be interesting to compare. Okay, other results can be done also for time-dependent problems like linear, semi-linear heat equations, etc. There are other things to do concerning Navier-Stokes and other systems when we speak of hierarchical control. Sometimes, instead of choosing two controls at the same level, as I have done before, it is interesting to hierarchize a little the roles of the control. For example, it could be interesting to fix F and V such that first, for any V, the associated f of v minimizes the functional, and then, in the second step, to choose v such that the couple v f of v drives the solution to 0. This is a very interesting Stackelberg, so-called Stackelberg hierarchical problem, in which at the same time you minimize an objective and you drive, at the same time you drive the solution to 0. You get the solution at the same time of an optimal control problem and of a controllability problem this way, okay? Etc. We can do other things, etc. And a problem that I have stated here concerns the time-dependent Navier-Stokes system. In that case, things are more complicated because, again, because of the lack of good results about existence and uniqueness. So there are things to do if you want to control from the bi-objective viewpoint. You want to solve a bi-objective optimal control problem for the Navier-Stokes. Okay. Let me speak a little bit about theoretical results concerning the controllability of Navier-Stokes. Okay. Very briefly, I will present this. On the theoretical control results concerning Navier-Stokes. There is a conjecture by Jacques-Louis Lyons many years ago, that says that the Navier-Stokes equation is at the same time with controls on the boundary is at the same time approximate controllable and null controllable. This is a conjecture. There have been a lot of partial results in order to intending to give an answer to this conjecture, but all of them are partial. All of them are in the positive sense, so all of them approach to the positive answer of the conjecture, but for the moment the problem is open. It is unknown whether the equations are globally approximate and null controllable. It is unknown. Among all the provided results, there is one relatively recent, due to Coron, Marbach, and Sueur, that says that the answer is yes if we change the boundary conditions. If instead of assuming u equal to 0, where we do not put control, we assume that the wall are the fluid can slice on the water. This is called a slip condition. It says that the fluid can slip over the wall, and this is called, well, this is a generalized Robin condition that says that more or less that the stress tensor, the normal stress tensor, more or less, normal stress tensor is given by the tangential velocity. It's proportional to the tangential velocity, something like this. So if these are called slip conditions, or more generally, Navier slip conditions. And with these conditions, they were able to prove the global results. Okay. This is a visualization of the situation. We start from this point. So if we do nothing, this is what we find. This is the desired target. We want to reach this point. So the question is whether or not we are able to change the control in order to get exactly at capital T at this point. Okay. This is the argument that they use in order to prove the result. I have not time to present it, but it is written. It is very well written in their paper. So this is the argument. most important part of the argument is to separate the behavior of the fluid near the boundary and far from the boundary. With the conditions that they have imposed, it is possible to govern the behavior of the fluid in both regions. With Dirichlet conditions, it is not clear. With Dirichlet conditions, it's not clear if the strategy that they have followed works. So the same thing has been said recently by us for Boussaada and other similar equations. And there is a list of problems that I think that are interesting, all of them concerning the same question. The first one is what happens with dynamic boundary conditions. For dynamic boundary conditions, we have more or less the same thing, but there is a time derivative here. And with dynamic boundary conditions, the problem is open. It is also open if you assume that the density is not constant, for variable density in Navier-Stokes equations. And also for a kind of what is called the true Boussaada system, in which we find a term in the right-hand side of the heat equation. So there are many questions around the conjecture that probably can be at least partially solved with the same arguments. And I'm going to finish with a linearized Alder system. This is another variant of Navier-Stokes equation. In this case, we have a term on the right-hand side that is a tensor. This is the dimensions of the tensor that is called the extra elastic tensor. Alder systems hold for what is called viscoelastic fluids. Viscoelastic fluids are fluids for which viscosity is important. This is the reason of this term. But it is also important, you also have elastic forces between the particles. The particles behave as elastic balls. So the elasticity, which can be considered something synonymous of memory, elasticity is important in this system. And elasticity is measured by tau. And tau is a tensor, what is called the elasticity tensor, that satisfies a hyperbolic, non-scalar hyperbolic equation of first order. So, and this is linearized Alder system. Okay, for linearized Alder system, that is, for example, the system that models the behavior of painting. For the linearized Alder system, we know things. We know that approximate controllability holds with the control on the right-hand side, also with the control on the boundary. Approximate controllability holds, but we also know that in general, null controllability does not hold because of the presence of memory, and memory avoids the null controllability. So for these kind of systems, the computation of an approximate control is an open question because you know that it exists, but you know that if it approaches the solution very near to the target, probably it's explosive. So it is a difficult question. And finally, I have shown the linearized Alder, but the linearized Alder stems from an original nonlinear problem that it is one. And this problem, for this problem, situation is completely open. Nobody knows what is inside. Okay? Thank you. And